thanks for invitation and thanks for the introduction. It's my pleasure to give a similar talk on the joint similar between among the Caltech, UCLA, and the USC. So today I'm going to talk about the infinite many global weak solution to the isentropic system of the gas dynamic system. So this is the joint work with Min Chen from University of Pittsburgh and Alexis Vasseur from UT Austin. Okay, so my talk will follow this outline first. I will give some introduction. In this part, I will describe the governing equations and then talk about the weak solutions to the incompressible Euler equations. And in the second part, I'm going to talk about how to construct the infinite many global weak solutions to the compressible Euler equations. In this part, I will introduce our main result and present the key idea and key steps. Okay. Yeah. Okay. So now let's look at the governing equation. So this is the Navier-Stokes equations. In particular, this is the compressible Navier-Stokes equations. Here, rho is the density, u is the velocity, p is the pressure, mu and lambda are the viscosities. So for the mu lambda term, we call the diffusion terms. And for this Navier-Stokes equation, the first equation is kind of the conservation of mass, and the second equation is the momentum equation. So roughly, the momentum equation can be viewed as the Newton's second law, as the application of Newton's second law in the fluids. So which means the left-hand side is the mass, the mass times the product of mass and the acceleration, and the other side is the total force applied to the body. Okay, so here for the compressible case, we choose P equal root to the power of gamma. In physics, gamma usually gamma bigger than or equals 1. When we choose the mu lambda equals 0, the compressible Navier-Stokes equation will be reduced to the compressible Euler equations. The compressible Euler equation is the oldest equation or the oldest system of the conservation laws. Okay, so since I want to talk about the compressible case, so let me spend one slide to discuss the incompressibility condition. So roughly say we can use this picture to show the difference between compressible and incompressible case. So the left picture is the incompressible fluids. So which means when the time change, when the pressure change, the fluids may change the shape, but the volume keeps the constant. So which means from here to here, keep the same volume. But for the compressible case, when the pressure changes, the volume also changes. So in that case, we call the compressible fluids. So for the in the mathematically, we can use the divergent u equals 0 to describe the incompressible condition. So when we choose rho equals constant, then the system will be reduced to the following one, so which is the classical incompressible equations. Okay, so now let's look at several questions in the fluid equations. There is a long-standing open question, which is to consider what kind of degree of the regularity to guarantee the uniqueness and the conservation of the energy of weak solutions. So the uniqueness is still a big open problem. The conservation of the energy, what kind of degree of the regularity is, or this problem is related to the Oscar conjecture. The Oscar conjecture was already proved, and so on the other hand, to look at this problem, we can say when the degree below a particular critical value, the uniqueness and the energy conservation may fail. So that means that motivated us to consider, can we construct non-uniqueness weak solutions, or infinite? Can we construct infinite many weak solutions? So this direction, the research of this direction can help us to narrow down the class of weak solution to single out the uniqueness condition for the weak solution of the Euler or the Navier-Stokes equations. Okay, so let's look at the incompressible Euler equations first. So this is the incompressible Euler system. Here, UP, the solution UP is to the if the UP is a solution to the incompressible Euler system. When the solution is sufficiently smooth, for example, if the solution is with the regularity is above C1, then the total kinetic energy EU is conserved, which means the EU does not change in terms of time, and the solution will be uniquely determined by the initial data. So here is a conjecture that is uniqueness should fail when the U in C alpha, if the alpha for particular alpha less than 1. So this is highly related to the Oscar conjecture. So we know the Oscar conjecture that is alpha equals 1/3, between 1/3 conserves the energy, less than 1/3 is energy dissipate. So for the Euler equation or the Navier-Stokes equation, for the incompressible case, there is a convex term. So for this term, divergent U term, right? So when we derive the energy inequality, roughly say we use U to multiply the momentum equation and take the integration by parts. But for the weak solution, when the regularity below a particular value, we are not able to process the integration by parts argument directly. So look at this term. So because here we have divergent U equals 0. So which means there is one gradient 3U. So if we put this distribute this gradient in 3U, so each one is 1/3. So that means if for the quantity, this quantity, the red quantity is can be controlled, which means 1/3 gradient U, the power of 3 is finite. Then we are able to do the integration by parts. So any better regularity would be sufficient to justify the integration by part to show this term equals 0. When this term equals 0, there is no energy dissipation, which means energy conserved. So based on this this observation, so Oscar conjecture every weak solution in C alpha, if alpha greater than 1/3 conserves the energy, and when the alpha is less than 1/3, when alpha is less than 1/3, so the energy the weak solution does not conserve the energy. Okay, so that's the Oscar conjecture. So now let's review the results related to the energy conserve or energy dissipation and the uniqueness. Look at this picture. So definitely when the solution is in C1, there exists a uniqueness, but we do know what's the alpha. When U is in C alpha, alpha should be less than 1, bigger than 0 somewhere. So we do not which what's the exact value. The solution will be non-uniqueness. So that is a non-uniqueness results. So there are a lot of non-uniqueness results. And for the Oscar conjecture, so the critical value is 1/3. So this part is the energy conservation of energy results, and this part is energy not conserved. So energy conserved, the main tool is commutative lemma to handle the weak limit and the nonlinear term. And for the energy not conserved part, the main tool is the convex integration tool. Okay, so that's the quickly review for the similar problem for the incompressible fluids. Okay, so now let's move to the. So now let's move to the compressible case. So here let's look at the So let's look at the results for the incompressible case. So the result. So this is the Cauchy problem for the incompressible Euler equations. So definition, and here's the energy inequality, and here's the result obtained by the Shigehide-Whitman in 2012, and we can provide another proof for this result. Okay, so this result say when for any given U0 in L2, so we are able to find a density V0 such that each V0 the initial data choose V0 as a new initial data. So for each E0, there exists an infinitely many global admissible weak solution. So here, admissible means the energy inequality. And for this result, the proof the two key steps. The first key step is construct a subsolution by vanishing viscosity limit from the Navier-Stokes equations. Since we know the Lehhoff theory is well known for the Navier-Stokes equations, but there's no result, global existing result or same for the incompressible Euler equations when in 2 or 3 dimension space. But when the viscosity tends to 0, which means the inviscosity limit, the weak limit is not commutative with the nonlinear term, which means we are not able to get the solution from the by the vanishing viscosity limit from the Navier-Stokes equations. Also, when the viscosity tends when the viscosity vanishes, the system will be reduced to the Euler equations. So this step, this step can provide a subsolution. So then we can apply the convex integration to a subsolution to generate infinitely many global weak solutions. So that's the idea for the for this result. Okay, so now let's look at the incompressible case. For the incompressible case, so this is for the compressible case. So now let's look at the compressible case. This is the compressible Navier-Stokes equations. So P equals root to the power of gamma, which means P satisfies the gamma law formula. Okay, so these two equations satisfied in the distribution sense, and the solution satisfies the energy inequality. Okay, so for the compressible case, for the compressible Euler equation, there are also some results related to the tool, convex integration tool. So the originally this kind of problems proof related relies on the convex tool and convex integration tool developed by Deleuze-Shigehide. And there are several directions of the isentropic flows. One direction pioneered by the Shirodori, and the other direction pioneered by Shirodori, Deleuze, and Cameron. They focus on the initial data value being Lyman data, so which means related to the one-dimension conservation laws. So I will spend another slide to discuss this the Shirodori Deleuze's paper. Okay, so here we defined the so we call this kind of solution, this kind of weak solution, as a admissible solution, which means here the solution satisfies the energy inequality. Of course, you know, in generally for the compressible system, in general the admissible solution means that the entropy solution. But here we use the energy inequality to replace it. If without if there is no energy condition, which means just the solution just satisfying the distribution sense without the energy inequality, the non-uniqueness solution can be constructed for any fixed initial data. You can say the Vasseur's groups work. Okay, so here our goal is to construct the non-uniqueness solution for the weak solution with energy inequality. Okay, so now let's let's look at the Deleuze's work for the 2D compressible Euler equation with gamma equals 2. So they proved that there are infinitely many bounded admissible solutions with the following initial data. So they assume U0 has two different values, U minus U plus, when x2 less than 0, greater than 0. They assume that the initial data U0 is a constant on the U1 on the U1 x1 direction. So essentially, so this kind of one-dimension space, because they try to rely on the try to apply on the classical theory of the 1D conservation laws. Since we know there's no there are not many theory available for the 2 or 3D conservation laws. Okay, so the key idea is similar. So the first step, construct the subsolution, and the second step, apply the convex integration tool to the subsolution to generate infinitely many solutions. Okay, so that means here P minus P plus that is related to the initial data, and then there are different fans P1, P2, possible Pn. So for each fan, we can apply the classical theory in 1D conservation laws, RH conditions to show the existence of the shock. So that means in each Pi, for example, in P1 or P2, so there is ρ I, Ui. So ρ I in P1, the ρ1 will be 0. In P2, ρ2 will be another, in P1, ρ1 will be a constant. In P2, ρ1 will be another constant. Either ρ1 is different from ρ2, but they are the constant. So if ρ is a constant, then the compressible Euler equation will be reduced to the incompressible Euler equation. So then they can apply the oscillation lemma, which is the lemma for the incompressible Euler equation. Because in each pi, the system will be reduced to the incompressible Euler equation. So they can apply the this lemma for in each pi. So the add each solution together, U1, U2, add them together. So by this way, so we call this is a subsolution. Then we can apply the oscillation lemma to the subsolution. Then that means U will be U plus U bar plus underline U. So U bar is a subsolution. Underline U, that is the infinity many bounded maps. So that is exactly solution of the Euler equations. So we are able to get the infinity many global weak solution. So this is the key idea of the CDK's paper. Okay, so we can get some viewpoint from this paper. So in that paper, they constructed the solution U, which is given by U bar plus the underline U. So we can view it as the mean flow plus flux stream. So this motivated us. We can rewrite the compressible Navier-Stokes compressible Euler equation, rewrite it as the following one. So if we are able to show a solution to this kind of equation, we call this solution is a subsolution to the originally compressible Euler equations. So that means if we are able to show a solution to this one, then we get a subsolution. So then we just need to find a suitable. Convex integration tool to apply the subsolution. Then we are able to get the infinite many solution. Okay, so look at this system here. Rho is still rho. U bar is mean flow. So here is R. R is a symmetry positive matrix. Okay, so particularly R can be written as this form. So this is a matrix. Okay, so based on this one, so we will have the following main result. So we need to restrict gamma between greater than 1, less than or equal 1 plus 2 over n. Here n is a dimension. That means when we are in 2 dimension, gamma need to less than or equals 2. When we are in 3 dimension, gamma need to less than or equals 5/3. So for any given initial data, rho 0, U0, if the initial energy is finite, which means this E is in L1, so there exists infinity many. So there exists infinity many rho 0 V0. So such that rho 0 V0 satisfies this kind of restriction, which means this kind of initial data is very close to the given initial data, and for this new initial data, for each new initial data, there exists infinity many global admissible weak solution, rho V to the isentropic Euler system. Here, so admissible solution, which means the weak solution plus the energy inequality in the integration form. Okay, so here we have to restrict our the value of gamma is 1 to 5/3 in 3D, but fortunately, the most interesting range of gamma in physics is this range, which means bigger than 1, less than or equals 5/3. Okay, so this result can be regarded as a compressible version of the one obtained by Shigehide Waitman in 2012 for the incompressible Euler equations, which so I mentioned the result at the beginning of this talk. Here, okay, so here our admissible condition is defined in the integration form of the energy inequality. In particular, the energy is decreasing in time of t. Okay, so the as what I mentioned before, the most interesting admissible condition for the compressible flow is the entropy condition. So which means it's a local form of the energy inequality. So possible that's our next step or next goal for this kind of problem. Okay, so now let me talk about our key steps to prove our main result. So there are two key steps, which is similar to the previous this kind of problem. So the first step is to construct the subsolution and then apply the convex integration to the subsolution to obtain the actual solution to the compressible Euler equations. Okay, so here construct a subsolution, which means construct a solution, a weak solution for this system. Particularly here we need R is a strictly positive symmetric matrix. So to construct a subsolution, so our idea is to take the vanishing viscosity limit from the Navier-Stokes equations. Since we know the weak limit does not exchange the nonlinear term, the product of the nonlinear terms, we are not able to exchange the order of them. So this can provide the non-negative matrix R, but we are not able to get a strictly positive this matrix R. We just get a non-negative. So we need another idea to get the positive R. And also we need to develop a tool of the convex integration to handle the compressible version fluid equation. At least we need to handle the density, the variable density. Okay, so if we are able, if we have some results for these two steps available, then we are ready to generate or produce infinity many solution. That means we just need to put the subsolution V. If we call V is subsolution and V tilde is the oscillation part, we add them together to generate the solution to the isentropic Euler system. So that's the bigger ideas. Okay, so now let's look at step by step to look at the first thing. How can we construct a subsolution for the compressible Euler equations? So here, let's recall the existing result of the compressible Navier-Stokes equations. So as we know, the existence of global exists results of the Navier-Stokes equation for the in particular for the incompressible Navier-Stokes equation was established many years ago. But for the compressible case, is another different story. So the first result was obtained by Pierre in 1995 or 1996. He borrowed the idea, the normalized solution, from his joint work with Depender in 1980. So but his result needed the gamma bigger than 9/5, and later Vasseur improved the value of gamma, but still need gamma bigger than 1/2, which means for the viscosity are the constants. But physically, the viscosity term may be a function in terms of the density. With what I mean, the mu lambda possible are the functions in terms of the density rule. So in that case, the model we call that model as the compressible Navier-Stokes equation with the density dependent in the viscosity depending on the density. So degenerate viscosity model. So in that model, the first weak solution, global weak solution, was constructed by the Vasseur and myself in 2016, and later we have another result with D.D. Bahesh. So in our result, we can show the global weak solution for any gamma bigger than 1 with the larger initial data. Okay, so that's why we choose the degenerate model here, because here we just need a gamma bigger than 1. But on the other hand, later I will show you why we need, due to the technical reason, we need to restrict the gamma less than 5/3 in 3D. So we okay. So when we let the viscosity tends to 0 up to a subsequence, so the solution, the weak solution of the Navier-Stokes equation tends to weakly converge to rho v. Okay, in some LP space here is weakly converge to. Okay, so we call this the weak limit is rho v, and then we can say here we have the matrix R and a scalar little r. So if put this r little r here, so we can say the v square over rho, this is for the Navier-Stokes equation solution, and this is the weak limit. That is also weakly converges to this term. So this is trace r, and then we can look at the energy inequality from the Navier-Stokes level. Then we have the weak limit satisfies this inequality. So this E0 is the initial energy of the Navier-Stokes equation. So we call this kind of solution rho v capital R little r as a subsolution of the compressible Euler equation with the energy inequality. So, but here we know this capital R or this little r, we just know they are non-negative due to the convex property, but we do know they are strictly positive. If we want to apply the integration, if we want to apply the convex integration, we need this is strictly positive. So we need additionally mathematical treatment to get this matrix is strictly positive. Okay, but I skipped the detail here. Okay, so after this step, we have a subsolution, but we still need some oscillation lemma for the compressible version of the variable density. So here is our oscillation lemma. So there exists infinite many V tilde and traceless U tilde satisfy this kind of restriction. Then so because this V tilde there exists infinite many, right? So this capital V, so what is capital V? Capital V is a subsolution which was obtained by the last step. So V plus V tilde need to satisfy this restriction. So you will see, because this kind of two restriction, so then we are able to show V plus V tilde that is exactly a solution of the compressible Navier-Stokes equations. Okay, so that means we have a subsolution, and so we have a subsolution. Then we have an oscillation lemma. Then we can apply the oscillation lemma to the subsolution to get the infinity many solution. So that's our key ideas. But here we need to mention another very important thing is, as what I mentioned, if there is no energy inequality, if there's no energy inequality for any initial data, Vasseur group proves that there exists infinity many solution, right? So, but if without energy inequality, so we just apply, then we just apply the oscillation lemma to subsolution, then we can get to infinite many solution, because V is subsolution and V tilde is infinite many V tilde. So add them together is a solution. So there is infinite many solution. But this cannot guarantee the energy inequality. Okay, so the last couple minutes. So now let me explain how to keep the energy inequality for the infinite many weak solutions. Okay, so here W0, ρ0, V0, R0. So we call this is a subsolution. So for this subsolution, so we can apply the convex integration to get a infinite many solution, which is called ρ V hat. Okay, so for ρ V hat, so we are able to get the energy will be given by E ρ V plus half trace R. ρ V is a subsolution, which is a weak limit from the vanishing viscosity limit from the compressible Navier-Stokes equations. But this guy here we have half. So look at this red term. So this guy is different from this one. So this is the end. So that means the energy is will dissipate here. So but we need to control them. So that's why here we need gamma is less than or equal 1 plus 2 over m. Because if we have this restriction for the value of gamma, then we can control these two red terms. One is less than or equal the other one, right? Then we can keep the energy inequality. Okay, so here we need to construct a new function, which is called RCT. So RCT, you can say RCT, this is a function only depends on time t. So that means this guy is divergent free for x. So that means we can add their RCT into here. So this W is still a subsolution because for RCT there is a divergent free. So at the beginning, so I already discussed for the look at here for W1 is low V R capital R little r. This is a subsolution. So for this solution, definitely we can apply the convex integration to generate infinite many global weak solution. But this kind of solution, we do know they satisfy the energy inequality or not. Okay, so here we add this term, the red one, RC, so that is still satisfy the energy. This W are still satisfy the structure of the subsolution, which means we still call this one is a subsolution. So you will find the energy satisfy this one. Then we can choose here a particular point T0. So here's a capital T. This T0 need to set is less than this capital T. So capital T is a short time. Is related to the local strong solution, the local time. Okay, so the T0. So we for V low V is a subsolution. So we can find the low V's value at T equals 0 and T equals T0 for this subsolution. So which means this subsolution low V we have two fixed value. One is T equals 0, the other is equals T0. So this is still a subsolution. So for this subsolution, we can apply the convex integration between T equals 0 and T equals T0. So then we can get a low V hat. So this solution, low V hat, definitely this value at the point T0 equals the subsolution. Okay, so then between T equals 0 and T equals T0, we have infinitely many solutions. But for this solution, some of them, the energy possible is increasing, some of them is decreasing, some of them is energy conserved. So we can show there are infinitely many time T tilde. At this point T tilde, the energy is very close to the initial energy. So this kind of T tilde, we can choose them as new initial data. We can choose this kind of new T tilde as new initial data because this T equals T0 is very, very small. So definitely T tilde is also very small, which means it's very close to T equals 0. And this new initial value is also very close to the original initial value. So we get the infinite. So this step, we get the infinitely many initial data because there are infinitely many possibility of the choice T tilde. So we get the infinitely many data, but we still need to show how to get the infinitely many solution, right, for each data. So then this solution, sorry. Okay, so we get the so the next step. So we look at this point T equals T0. So we can choose this one as the initial data. So we apply the convex integration. We get an infinite many solution, which is called low V bar. Low V bar is there are infinite many solutions. But this guy as a with the initial data, the t equals at here. So we have we apply the two times the convex integration. One is between t equals 0 to t between t equals 0, t equals t0. The other for t bigger than or equals t0. But these two solutions, they share the same value at t equals t0. So which means we can grow all those solutions together at the point t equals t0. So grow them, after growing them together, they can view as one solution on the whole line timeline, which means is from here from t theta to possible in the anywhere for any positive time. So because low hat, we have an infinity low hat, infinity many low hat, we have infinity many v hat, and add them together, so we have infinity many global weak solution. Okay, so that's our key idea, and how to keep the energy inequality for the global weak solutions. Okay, so thank you very much.